All right. So this session is Kubernetes networking at scale. And I am Bowei. I work at Google.
And I'm Laurent. I work at Datadog in the team responsible for operating Kubernetes cluster. And we run pretty big Kubernetes cluster. We run whole different kind of issues with networking, and this is one of the feedback we give.
OK. So in general, we're looking at, to give a concrete data point for what we're going to talk about in terms of scaling challenges. So we're talking about thousands of nodes, dozens of clusters, and each cluster having tens of thousands of pods and then thousands of services. In terms of the application that we're looking at applications that process, say, trillions of RPS and gigabytes of data per second. In terms of topology, we're talking not just of single cluster or communication within a single cluster, but communication across clusters and from VMs and clusters, mixing them. And finally, in terms of latency, we would like the lowest latency possible for these workloads. Now, in terms of the high level, looking at scaling challenges, we need to consider a couple of things. First is, in the data plane, you really want to remove as many inefficiencies as possible, right? Kubernetes offers a whole bunch of abstractions, but we really want to reduce the cost of those abstractions. In the control plane, when you're scaling up your cluster, you will hit these large N issues, where N is number of nodes, number of resources. In addition to the large N issues, you will also want to simplify your architecture. Simplifying your architecture really means reducing dependencies and making it easier to debug. And in general, we have found that the strategy to do this is to kind of enable more native integration with the infrastructure that you're running on. Now, let's see what this means in practice. So we'll talk about pod networking. We'll talk about service load balancing. We'll talk about L7 load balancing, which is Ingress. And then finally, we'll discuss DNS. So first, let's talk about pod networking.
Pod networking is the way to give interfaces and IP addresses to pods. There are many different ways to do it. The most simple one that many people have tried when they get started is to use static routes. So the way it works is you give every node on your cluster a CIDR, and then you use the cloud provider routing table, and you add static routes for each CIDR pointing to the nodes. This is very simple, works fine. However, there are limits in terms of number of static routes. For instance, by default, on AWS, you can't have more than 50 static routes, which means you can have more than 50 nodes. And also, and we'll dive into this later, it's not very efficient in terms of address space, because if you give a /24 to all the nodes, if you have 10 to 20 pods per node, it's not going to be very efficient, and you're going to consume a lot of address space, and it's going to be tricky to manage. Another option is to use overlays. So this is, I think, where most people are at today. By overlays, I mean either Calico or Flannel, for instance. And the way it works in that case, you also allocate a CIDR for each node. But instead of relying on the cloud provider routing to get traffic, pod traffic from one node to another, you actually create an overlay, which means all these CIDRs you've allocated to nodes are actually virtual CIDRs, which means the underlying network doesn't know anything about it. And the way it works is you actually do tunneling using either VXLAN or IP-IP. This works fine, and it's very efficient because it means routing is going to work regardless of the underlying infrastructure, which makes it very easy to set up, and that's why it's very popular to do it this way. However, there's quite an overhead in tunnels because you need to create packets, and you need to add the additional header for them, and also distributing the route is sometimes a bit tricky. So here is a typical example of how that would work. Your pod would get an interface, so a VF interface connected to a bridge, and then you would have a VXLAN interface connected to this bridge that's actually getting traffic out of the node. So in this example here, I'm getting traffic from one pod with IP 192.168.0.1 to 192.168.0.8y, okay? And on the wire between the two instances, you get traffic between the node IP, so the one in 10, both IP in 10. And the original layer 2, so sent by both pods, is actually encapsulated in that VXLAN header. And as you can see there, like, there's a cost because you have all this additional information in the packet, and also creating the VX line frame is consuming in terms of kernel CPU usage. Another issue with control plane, I mean, having overlays is fine when your number of nodes is not that big, but at a certain scale, it starts to be tricky because, as you can see in this example, it's a typical deployment of an overlay. You have an agent on the node that is going to configure routes and tunneling, for instance, VXLAN in that case. And this agent needs to get information on the cluster, so it's going to connect to the API server. And quite often, it's going also to need a data store to store all the information it needs. It's quite often etcd. And as your number of nodes grows, the load all these agents are going to cause on data stores, and API server is going to be non-negligible and can become an issue. So in terms of best practices, what we think where everybody is going is to use native pod routing, which means avoid overlays. In this case, we want to have all pods to have routable IP on the network, and so no overlay. It's much easier to debug, it's simpler, and also it allows for a flat network, which means communication between two clusters, pods in different clusters, and even VM outside of your cluster to your pods is going to work because everything is routable. Another optimization that we're seeing more and more, and we're relying heavily on it at Datadog, is remove bridging. Like a typical installation is the one I showed you before, where all pods are connected to a bridge and then routed outside the host. But when you think about it, you actually don't need this bridge quite often. You just can rely on the host routing itself. And this is what we do most of the time. Another optimization that is that we see quite often is IPVLAN, where it's even faster than having routing. So you remember the slide from before. You can see that this one is much simpler because in that case, all pods have routable IPs, and they are in different space than the IPs of the nodes, but everything just works, and it's much more efficient. In terms of, so this is a principle, and now we're going to talk about how this is done in practice. So we're going to very quickly talk about on-premise. On-premise, sometimes you're very lucky because you can actually control the network, and you can establish BGP connection between your nodes and the network, which means the network is going to know about the CIDR allocated to each node, and it's going to be transparent. It's just going to be another CIDR. In cloud provider, it's slightly different. So let's first talk about how it's done at Google.
Okay, so in the Google Kubernetes engine, or if you run Kubernetes directly on GCP, it used to be in the old way that we create these static routes. Now, as we discussed before, static routes, the static route functionality is actually fairly complex, and you can easily run into quota issues because it's somewhat resource intensive to sort of implement all the different features there. What we have added is a VPC native mode. So in VPC native, you have a pre-allocated range for the pods. And from this range, the cloud actually allocates the IPs as alias ranges to the VMs. And the cloud actually manages this IP allocation for the cluster. Now, this is much more semantic and efficient for the underlying SDN. And in fact, you're telling the SDN about the pods. So the SDN kind of knows that there is this range allocated to the pods, and the SDN also knows about this allocation to the pods itself. So let's see how this works. So in classic Kubernetes, you have a range that's devoted to the VM IPs. You have this pod IP allocation, and then you have the service IPs on the left. And then with the VPC native mode, the cloud will allocate these /24s to the various nodes that come up in your cluster. And in fact, because we have delegated IP allocation to the cloud, we can do interesting things like have the cloud control the size of this allocation to various nodes. And actually, this becomes a scalability issue as well, that Kubernetes, I'm sure everyone has noticed, when you create a cluster with the default settings, it's actually quite greedy in terms of eating up your IP addresses. For instance, with the default settings, 1K nodes with a /24, well, that's 1,000 times 256, which is actually 256 IPs on your network. And we find that a lot of people, when they try to stitch their networks together, actually run out of space. So with the cloud-mediated IP allocation, we can tell it, oh, hey, I don't need that many IPs. This is a node that's going to run a very specialized workload. We can give it fewer IPs, so you can kind of right-size it for your node footprint. And in general, we hope that sort of as future work is that we get away from these contiguous ranges and basically go to discontiguous ranges that can be merged together so we can kind of have clusters that fit into your network footprint. Another interesting thing about VPC native sort of cloud SDN integrated pod routing is that there's an opportunity to give the SDN full visibility of your traffic. So when you create a VPC native cluster, you can, when you see that when a pod talks to another pod over the SDN from node to node, the VPC is able to see the flow. But when the pod talks pod to pod, actually this flow is not visible to the SDN. Well, you can play some tricks with the PTP to basically pin that traffic out to the SDN. And what this means is that all of your pod traffic, whether it's between nodes or within a node, will be visible by the SDN and kind of use the same infrastructure. For example, you can use the same kind of tools on your SDN to observe all the flows in your cluster.
So this was for GCP. On AWS, it's slightly different because there's no equivalent feature in terms of IP alias range. You cannot associate an additional range to your nodes. But there are still some CNI plugins that allow you to give routable IPs to pods. So the first one that's pretty well known because it's the one provided by AWS and used on EKS is the EKS CNI plugin. The way this plugin works is you basically attach additional ENIs to nodes and additional IPs to the CNI, and this IP are going to be the pod IP. The way it works in terms of workflow is when the kubelet and the runtime are going to create the interface for the pod, the first thing they're going to do is the CNI plugin is going to call a daemon that is responsible for allocating ENIs and providing IPs. And then this runtime is going to create the interface, associate this IP with it, and do some clever routing on the host to make sure that traffic from IP1 on pod 1 is actually going to through interface ETH1 and not ETH0. An alternative plugin is a plugin developed by Lyft, which is very similar in terms of how it's designed, because it's also attaching additional ENIs and additional IPs. It's a bit more complicated because they did some optimization. So the first difference is it's daemonless, so you actually have a binary called IPAM something, and this binary is responsible for manipulating ENI and allocating IPs. And the main traffic for the pod is going to use an IP VLAN interface. The goal for this one is to be much more efficient than doing just routing, because IP VLAN, you don't have to cross the same part of the kernel, so it's going to be faster. This works pretty fine, but sometimes you also need to reach IP addresses on the node, such as the kubelet, for instance. In that case, you need an additional interface, and that's why there's this third plugin there called PTP, which is going to create an interface to the host. So this works pretty fine. We've been using it for more than a year now, and we've been very happy with it. But honestly, it's a bit complicated to debug sometimes. As a conclusion on this part, native pod routing is very efficient. We're pretty sure that everybody is going to go this way in the future. You don't pay the cost of the overlay. CNI plugins are still a bit young, but they're getting there. I mean, we've seen a lot of progress in the last year. And as I was saying before, it allows for traffic between clusters and traffic with VM, so it's a lot easier. And finally, it allows Ingress traffic to be managed much more efficiently, and we'll discuss this later.
Okay, so let's talk about service routing. So when we talk about service routing, we instantly get into the land of kube-proxy. To kind of give a sketch of how kube-proxy works, on every node there's going to be a kube-proxy instance. It's going to watch the API server. Associated with this whole service mechanism is a set of resources, which are controlled by the endpoints controller and the service controller. And the endpoints and service controller basically are responsible for looking at the service resources, assembling all the relevant endpoints, and writing them into this etcd that then can be consumed by the kube-proxy. Now, the kube-proxy implements a client-side load balancer on every node, right? So here you have the client, and it's sending traffic, and there's this proxier box. In most typical implementations with Iptables, that's actually just a Linux kernel, and then it's going to load balance traffic to the various pods. Now, the original implementation of kube-proxy was in user space. This is old history. Most people use the Iptables-based kube-proxy. It's default since 1.2, and it's way faster than user space, but we'll see that it has some problems. And then finally, there's an Ipvs implementation that went GA in 1.11, and it uses a different kernel mechanism, but it still relies on Iptables for some things. It's faster than Iptables, scales better, and Laurent will talk about their experience with Ipvs. So in terms of IP tables, what is it doing? So it has to make a load balancing decision on the client side. And to keep the traffic flowing, it has to handle two cases. It has to take the outgoing traffic, find a backend, rewrite the backend, the service IP to the backend, and then also handle getting the traffic back in the reverse path. And the way this works, I won't go into detail, but it's a lot of chains of IP tables, right? And generally speaking, IP tables is, the rules are basically a bunch of if statements chained together in a linear list. So if you first have to select a backend, and then you have to go to a service, and then you have to traverse all these tables. And generally speaking, it's a long chain, and especially when you have a lot of services and a lot of backends, these chains grow linearly with that. So what are the challenges? Well, a couple of, and I kind of hinted on it in the previous slide. The IP table's kernel interface requires a sync of all the rules in one shot. This is just how that kernel interface works. You have a longer sync time. Now, this used to be a big problem, but some kernel fixes went in and it has gone down to seconds, but it's still, you have to pay that cost. And there's significant memory usage. Because you have to generate this list of rules, it has to, even if you're changing one thing, generate the whole list, which may be in a large cluster over 100 megabytes, sync it, and then you continue. The second thing is IP tables uses contract, which leads to a lot of right-sizing issue, right? How much memory do you have to reserve for contract? And we have seen this especially challenging when you have DNS traffic, which consumes a lot of contract entries. Finally, just as like a future-proofing note, this is basically whatever you see in Kubernetes in terms of load balancing is basically everything you could do with the IP tables. And it's very hard to conceive of adding additional functionality.
When we started our journey in Kubernetes, we knew our cluster were going to be big in terms of number of nodes, number of endpoints, and we knew we were going to have issue with IP tables. So from the get-go, we decided to try Ipvs because we assumed it was going to be a lot faster and a lot more efficient. In terms of design, the logical design is the same one as we used before. And in terms of mapping, in terms of components, a Kubernetes service is mapped to a virtual server in Ipvs and a pod as a real server, which is a backend in a virtual server. So as Bowei was saying before, the main advantage here is that updates are atomic. So you only change, if you delete a pod, you only need to update the backend in a virtual server. So it's much more efficient. In terms of how it looks, this is the output of the Ipvs ADM command, which is giving you information of what's configured in Ipvs. As you can see that this is a service IP for an HTTP service. And you can see two backends using port 5000 in this example. Ipvs has been working pretty great for us. We've been using it for more than a year, as I was saying. But there was one change that was very important and that made things a bit tricky over the last few months. Ipvs used to not support graceful termination at all, which meant as soon as you delete a pod and a pod becomes not ready, it's removed from the backend, which means no traffic is going to flow to this pod anymore. Which when you have an existing connection open, you would want sometime, for example, for HTTP, you would want for the end of the communication to go on, which is a lot better. So graceful termination was introduced in 1.12 and backported to 1.11. And the first version of it had a few bugs, but we're getting there and it's a lot better now. So if you have any issues with Ipvs, please let us know open issues on kube-proxy. We'll fix it. We're really committed to fixing it. One thing that's important with Ipvs is we have double contracting. Ipvs has its own connection tracking system, and you also rely on the contract in the kernel. And it's a bit tricky because then, Bowei mentioned issues with contract sizing and timeout before. So now we have to do it twice, both in Ipvs and in the normal contract. And the default timeout for Ipvs are not great. The figures there are for TCP, TCP fin, which is when a connection is terminating, and the 300, so 5 minutes, is UDP. As you can imagine, keeping a connection in the contract for 5 minutes when it's a DNS query is a pretty bad idea. We also had a few issues with CNI because most CNI plugins are tested with IP tables, and routing with Ipvs is slightly different. So we've noticed some weird interactions. So if you want to try Ipvs, make sure that you test everything with CNI too. So kube-proxy is one of the implementations of client-side load balancing. There are several others. Kuberouter is one of them. So kuberouter is doing a lot of things if you know it. It also allows you to control routing between your pods. And it comes also with service load balancing using Ipvs, and it's a different implementation. Another option would be to use Cilium, which is using eBPF to do client-side load balancing, and in addition to, and has many other features in addition to that.
Okay, so just to wrap up on the service load balancing, there's actually a couple of other exciting things going on. So first is implementation of topology-aware service routing. So what this means is like you can express things, for example, load balance first to my node, and if that's not available, then spread it out across the cluster. And that's the link to the KEP. And please take a look at it. It's pretty much implementable, but we really would like feedback. The second is, I'm sure if you run in a big cluster and run big services, you'll notice that eventually your endpoints object will become super massive and no longer fit in your etcd table. So this project, Endpoint Slice, is a project to take that endpoints object and shard it among several endpoint slices to get around this scalability issue. So please take a look at that KEP as well, because that is an ongoing design.
The third topic we're going to talk about is ingress traffic. The first way to get traffic inside a cluster is to use a load balancer type service. In that case, this is how it works. So you create a service of type load balancer, and the service controller in masters is going to provision a load balancer on your cloud provider, and this load balancer is going to send traffic to node ports. And the typical flow of traffic is going to the load balancer, hitting the node port on a node, and then kube-proxy is going to take care of load balancing the traffic to the actual pod serving the application. It seems fine when you see it this way, but the first thing is it's not very efficient because it's very unlikely on large cluster that you're going to hit a node where the service is actually located. So you're going to first hit a node and then be routed again to a new node where the pod is. Another issue is that if you have a large cluster with very different workloads, for instance, a Kafka or a Cassandra cluster, you wouldn't want this node to get a part of web traffic, for instance, because it's really not efficient, and you wouldn't want another traffic to impact traffic of a very critical data store. An option is to use external traffic policy local, in which case kube-proxy is only going to send traffic to local pods, and it's going to fail the health checks if there's no pod on the service. So this is much better than before because you don't have to do the additional hop. However, you still have a few issues. The first one is that if you have hundreds or thousands of nodes, all these nodes need to be registered with load balancer, and there are limits in terms of the number of nodes you can register with load balancer. To give you an idea, on AWS, this limit is 1,000. There's no way you can have more than 1,000 instances attached to an ELB. Another one, an issue we've seen in the past, is that health check are still going to be sent to all the pods, which means this is going to be a lot of traffic still already. We were talking about load balancer service, so L4 ingress. Another way to get traffic inside cluster is to use L7 ingresses, so the ingress object in Kubernetes. And it's actually exactly the same implementation when you look about it. The only difference in this slide is that these objects are not controlled by the service controller on the master, but on the ingress controller. But it's exactly the same flow and exactly the same issues. Another option would be to use Nginx as a proxy or HA proxy, for instance. And in that case, the right part of the slide is much more efficient because these pods are going to be configured directly to route traffic to relevant pods. So the traffic between the proxy and the pod is going to be very efficient. But as you can see on the left part of the slide, you still need to get traffic to these proxies, and so you need usually a load balancer service in front with all the issues we mentioned before. For this reason, we really believe that the future is to do native routing. In this case, load balancer route traffic directly to pod IPs, and this is of course only possible if your pod have native IPs in the VPC, which is what we were showing before. There are several implementations of this design. On AWS, for instance, you have a controller called the ALB ingress controller, and which can be configured to route traffic directly to pods instead of instances, so it's much more efficient. The way it works is it's creating an ALB, and the target group is directly targeting IPs. On GCP, load balancers can be configured to use network endpoint groups, which is going to do exactly the same and route traffic directly to pods. Proxy also do it, as I was saying before, but of course you still need to put something in front, and it's probably going to be either based on network endpoint groups or ALB in my example.
Okay, so now you notice that those cases cover some of the workloads surrounding L7 in Ingress, but what about L4 in ELB? So currently, there doesn't seem to be a solution there. And it's also limited to HTTP traffic. Now we want to consider UDP or TCP traffic. And so this is kind of a work in progress to get container native load balancing for all the different types of load balancing that we need. Finally, let's talk about DNS challenges. So this is a lot of people have run into this. So this is a summary of the DNS challenges that people have seen. So you have an application, let's say it's in Node.js or Ruby. And it does is get host by name, or hopefully the recursive variant. It has a search path, which means that the number of queries actually gets amplified quite a bit. And we hit the contract table because kubedns is going to be a service. So we may run out of contract entries. Now also, DNS is a UDP protocol, and who knows where that UDP packet went. So we might have lost it going to the query. And finally, because of this search path amplification, you may not have enough instances to soak up all this load. So there's a whole slew of problems associated with the volume of DNS queries that we see in Kubernetes. So one of the solutions to this problem is to actually drop a node local cache into your cluster. So the node local cache runs on every single node, and it can, first of all, it's a cache, so it can absorb some of the queries right away. The second thing that it does is it avoids contract. It actually inserts special rules into your Iptables chains to basically skip contract and go directly to the node local cache. And finally, it upgrades all your connections. Instead of sending UDP, it sends TCP, which is a lot more reliable. And then finally, hopefully, it has reduced load anyways, so then you don't have these scalability problems with the number of instances. Another interesting thing, and this is an ongoing KEP, is that why don't we take care of that search path issue? So node local cache is a smart agent. We can put some logic in there, and it can actually coordinate with the upstream kubedns infrastructure. What if we have the node local cache insert that search path somehow into the DNS query, perhaps as an eDNS field, and then actually the search path mechanism could be resolved upstream inside the server, and you won't have to send all those packets over the wire.
Now I'm just going to describe you the way we do DNS at Datadog, and it's a lot inspired by the node local cache that Bowei mentioned just before. So this is the typical way we do DNS at Datadog, and a very standard one. So this is the default configuration. The kubelet is going to inject search domains, the endpoint option, which governs when there's going to be expansion of the searches. And so this works fine, but when a pod wants to do a DNS query, it's going to contact the DNS service, and it's going to use Ipvs, and it's going to go to the main system node, or all the nodes running your core DNS pods. And then the query is going to come from there, and if the core DNS doesn't know about this service, it's going to forward it upstream. As Bowei was saying before, this leads to a few issues, and we had quite a few outages for this design. So for applications that do a lot of queries, and I'm talking about thousands of queries per second, this design is pretty inefficient. So we introduced an alternative that's opt-in. So people can just add an annotation on their pod, and we have a mutating webhook that is going to modify the configuration, the DNS configuration of the pod. And you can see here the configuration of the pod. So we do two important things. The first one is we have a single search domain, which is going to be svc.cluster.local, which means even in the same namespace, application will need to put service.namespace. They can't use just service. So that's the reason it's opt-in. It's because it's breaking some of the Kubernetes contracts, but it's much more efficient because most of the time it's going to be a single query. In addition to that, because we are very opinionated in the way we do search domains, we can go back to endpoints equal to, which means if you do a standard query like www.google.com, this has two dots, which means there's not going to be expansion, and traffic can be, it's just going to be asked google.com and not www.google.com.service.cluster.local, which is typical expansion. We modify also the resolver in point to a node local DNS cache. Okay, so it's a very small core DNS instance running locally. And This instance does two things. It does caching. So if you hit the same name a lot, you're going to benefit from caching, so it's going to be a lot more efficient. And in addition, it routes traffic that is not resolvable by core DNS natively in the cluster directly to the upstream locally. So if the query doesn't end with cluster.local, it's directly routed to the VPC resolver in our case. So it's much more efficient, and we've had quite good results with it. And down the road, we're probably going to switch from opt-in behavior for this behavior to this behavior by default with opt-out for application that can't work with it.
OK, so in conclusion, really a common theme is removing the cost of all the abstractions, right? Native integrations with the infrastructure is key. So a lot of these things that we described, it's like, how do we get things to route directly? How do we remove overlays and so forth? One thing to observe is many kept in flight to improve scalability. And then the third thing is actually there are many interesting future technologies that haven't been explored yet in terms of the implementation. So for example, eBPF, maybe some integration with the service mesh. And then in general, I don't know if you attended any of the scalability talks as well, but the idea and where the community wants to go is to just make sure everything scales by default out of the box. I think one of the scalability talks talked a lot about SLOs. It's like, how do we get the implementation to such a state that we can kind of give you an SLO that you can rely on, even though your cluster is 5,000 nodes, 10,000 nodes. With that, the end of our talk. And by the way, thanks for staying, because this is the last talk on the last day. So.
And if you want, I think we have a few minutes for questions, and we're going to stay around anyway for a bit longer.
With the native approach, do you find like very rapid scaling, like large rapid scaling up and down of the cluster, and a lot of movement to pods to sort of cause additional problems?
So are you, like, is it AWS specific?
Yes, for me.
Okay, yeah. So yes, I mean, we don't have the issue that much because we don't increase the cluster size very fast. But yes, the way both plugins work is they locally try and get an address, and so you can get rate limited by the AWS APIs. So yeah, I think this can be improved in both the AWS and the Lyft plugin, but it hasn't been a problem for us. But we know we've talked to people that have had the issue too. And I think one of the ways to solve it is to actually pre-allocate IPs or a bunch of IPs to avoid all the instances doing the same thing at the same time.
I can answer this question for the network endpoint groups, actually. We had interesting technical challenge in terms of trying to batch things together so they can go fast. The code is actually open source if you want to check it out. I can send you a link. Any other questions? Yes, Chris.
As mentioned, part of the Iptables problem is like the n-squared ever-present networking problem and the linear search in Iptables. How is this helped by moving that into the load balancer or the neg implementation? Is it just a different data structure that doesn't require the linear search, or do you just scale it out in a different way?
I see. Well, you don't need that linear search because it knows the direct backend. So it can kind of, I mean, it can run a smarter data structure than just a linear list. That's one answer. I think that's like a big answer, actually. Because Iptables, you can use IP sets, but that's not currently the implementation. If you had IP sets, actually Iptables, certain aspects of it aren't linear anymore. But that just, it doesn't exist right now. It depends, although we'd have to look to see which parts that would be relevant for. Because I don't know if you can do that with the service. Like the service lookup for IP table could clearly be in a hash table, but with Iptables you have to put in a list.
And I think there have been a few discussions on how to shard the Iptable chain, but I think it's been discussed, but I don't think there's any implementation ready.
Another question?
So regarding the same Iptables issue, during the presentation there was it was mentioned that for IP tables you need to write a lot of long rules to route to route the network between two ports. And have you thought like using this service for doing that, for storing all the rules? And how have you tried to use OpenVSwitch for that?
Try to use OpenVSwitch. I see. That's an alternative implementation that I guess we haven't covered. It could completely replace IP tables. So in some sense, you're talking about a separate implementation. What was your first question? I see. The issue that was illustrated here, so the question is, have you thought about using a separate service for storing the rules? The issue that was brought up was more that the kernel interface to change IP tables is actually all just one shot. Like you have to generate the whole thing and put it in, even though your change might be very small. So that turned out to be very inefficient because if you have a lot of endpoints, a lot of services, you kind of have to regenerate that thing over and over again. If you cached it, you would still have the problem that you'd have to shove it through to the kernel repeatedly, even though you still have the thing generated. Any other questions?
So in the on-prem scenario, it's not always an option to be able to use the raw architecture IP addresses. And overlay seems to be the only solution, unless going for another address space and IPv6. So given what you know about Kubernetes at scale, is IPv6 an option to get those things?
I cannot answer your direct question, but luckily the dual stack KEP is in a pretty good shape. So hopefully Kubernetes will just work on IPv6 soon.
And for the on-premise question, most of the people I know, but I'm really not a specialist, what they do is they do native routing. They have BGP, so either KubeRouter or Calico running on the node. And all this during peering, to older BGP routers and announcing route to the network, in which case you don't need an overlay. If you can't do that, because in many companies you can't actually do that, then you have to use an overlay. But yeah, if you can, try and negotiate with the network team to make it happen, it's going to be a lot more efficient.
Okay, thank you for a great talk. I have a question. Just in case, did you try playing with Iptables, this new fancy firewall subsystem?
Yes, so someone mentioned Iptables, and it definitely solves some of the IP tables problems. I would love to see an implementation. Yeah. So if anyone is interested, I'm pretty sure the SIG would be interested in seeing an implementation.
One of the biggest issues is the kube-proxy contract today is pretty complicated, as we've seen on I've worked a little on the Ipvs implementation, and the contract established by the de facto default, which is Iptables, is very complicated, and getting this right in a new implementation is going to be tricky, and it's going to be a lot of work. So, if someone started, I'm sure the community would love to try and use it. But to be honest, Iptable is not a load balancing solution either, so it's going to end up with, it's going to be better than Iptables, but it's not going to be a client-side load balancer. The future is probably eBPF based for this, I think.
So you're using IPVS for a year, right?
Yes.
And is there any reason not to use IPVS now? It's not the default solution, so what are the kind of drawbacks? This graceful termination was a major blocker, I would say, but now it's apparently solved.
I'd say today, for most use cases, IPVS is stable. There's a few issues upstream, but nothing in terms of features. So there's one where the communication behavior is slightly different in IPVS and Iptables. For instance, you can do local host nodeports. This doesn't work. Other than that, most of the things work. The only remaining issues are related to graceful termination, and we decided 2 weeks ago to remove graceful termination for UDP, which is going to solve most of the ongoing issues. And since the Iptables implementation is not supporting graceful termination for UDP either, it's going to be the same behavior. So we had a few people that wanted graceful termination for UDP, for Quick, for instance, but it's very hard to get right. So we decided to go exactly as Iptables and remove graceful termination for UDP, which is going to solve most of the remaining issues. And once again, if you try it and have an issue, create an issue on the repo, and we're going to look into it.
Yeah, exactly that. So IPVS, I know some people had some issues because it puts the IP address on an interface, and that ended up capturing traffic, given how their CNI set up. So really, it's like you have to, it hasn't been battle tested. So it just needs wider usage, and then you can get the feedback and fix it. What's that? Well, it's battle tested for a vertical slice, right?
No, but yes, I mean, most of the new issues are related to edge cases that we don't know about. For instance, we had a lot of discussion with people from MetalLB, which does pretty clever thing that no one in the Ipvs team had tried before. And so we had to solve this, for instance. So it's like specific use cases, specific CNI implementations. So I'm sure we're going to get it fixed, but we need more usage to be sure that we're covering everything.
One more question?
So you mentioned on AWS the 2 CNI plugins, the official AWS one, yes, which also is used by EKS, and you are using the Lyft one.
Yes.
Do you have any elaborate comparison? What are the pros and cons, or know where to find this? And why is AWS barely creating a new one? And
so we started with the AWS CNI plugin because it seems to be the most natural thing to do. The first implementation was very young when we started, and it had quite a few bugs. We had to fix them, and the interaction with the team developing the CNI plugin was a bit difficult at the time, so we decided to try Lyft, the Lyft implementation, and it turned out this implementation was pretty solid, and it was very easy to get things patched upstream, so that's why we went this way. In addition, in terms of design, it's daemonless, which we find a lot better because it's simpler to just chain CNI binaries on the host. And honestly, I mean, we've been running the Lyft CNI plugin for more than a year now without any problem. Oh, we fixed a few things along the way, but.
Okay. Thank you all for coming. Thank you all for staying.